This is the video for Chemistry 1's lecture over average atomic mass. So when we measure atoms, masses, we don't measure in grams for the really simple reason is that they're just too small. No one has ever seen a single atom. It is so small, we can't measure it, so we just don't measure the mass of atoms in grams. In order to actually measure atoms, because we do need to measure it somehow, we created a scale based on relative masses, and we picked carbon-12 kind of as the standard. We said that carbon-12 weighs exactly 12 AMU, and AMU stands for atomic mass unit. When we say we picked this as our scale, that's kind of our starting point. We base every other atom to carbon-12. So when we set our standard to be this entire scale based around carbon-12, that kind of by definition meant that a single AMU, a single atomic mass unit, was 1/12 the mass of a carbon-12 atom. We said carbon-12 weighs 12, therefore 1/12 of that 12 is a single AMU. Now, when we created this scale, we didn't have the technology that we currently have today. We didn't have these super precise tools that modern day chemists and scientists use. Since we've had those tools created, we now know that 1/12 the mass of a carbon-12 atom is approximately 1.66 times 10 to the negative 24 grams. So we can measure it now with really precise tools. But back when we first needed the scales, they didn't have that technology. So don't memorize this big old, the fact that the atomic mass unit is that mass. Don't worry about that. Just understand that an AMU is 1/12 of a carbon-12 atom. That's why it's in red. So, based kind of around this idea of AMUs, a hydrogen 1, which has a single proton, has a mass of about 1 AMU. The only thing there is that one proton. It's the only thing there that has mass. So it's about 1 AMU. Now, if you want to get real specific, when you compare the actual mass of a hydrogen 1 to the actual mass of a carbon-12, it's about 1.007825. We, generally speaking, just round that down to 1. So atomic mass unit is essentially 1/12 the mass of a carbon-12 atom. That's our scale. Now, we've mentioned in the past that the mass number is not found on the periodic table. The mass number is the sum of the protons and the neutrons of an atom. It is a whole number. You cannot have a part of a proton. You cannot have a part of a neutron. So the mass number of every single atom or ion that we deal with is never going to be located on the periodic table. However, there are two different numbers in every single box on the periodic table. We know that top number represents the atomic number. In other words, the number of protons, the thing that makes that element that element. Carbon is carbon because carbon has 6 protons. That's that top number. The bottom number, the larger number, is something we call the average atomic mass. It is a weighted average, and this idea right here, weighted, is really important. We'll talk about it more in just a second, but it is the weighted average of all of the mass numbers of all of the naturally occurring isotopes of an element. So carbon-12, carbon-13, carbon-14. We do a weighted average, which we'll go through here in just a sec, and we come up with the fact that carbon's average atomic mass is about 12.01 as opposed to just 12. So when we actually go in and we start calculating these average atomic masses, we based it off how abundant these different isotopes are in nature. So, for example, carbon 12, 13, and 14, most of the carbon that we ever deal with in nature is carbon 12. It's about 94, 95% carbon 12. So that's going to be a much bigger factor in the average. And that's what makes these averages a little bit different than what a normal average is. Normally when you take an average, you add the three parts together and you divide by the number of things you added together, right? If I take 3, 4, and 5, the average is going to be 4. 3 plus 4 is 7, plus 5 is 12, divided by 3, because you added 3 things together, gives you 4. A weighted average is a process or method where we say one of those numbers is more important than the others. For atoms, we base that off of abundance. Like I said earlier, the more prominent, the more often it occurs in nature, the more it gets added together into the average. Again, jumping back to carbon-12. Carbon's average mass is 12.01, even though there's carbon-12, carbon-13, carbon-14. What that tells us is that there's so much more carbon-12 in nature that even though there are these other carbon-13s and carbon-14s, most of that average is going to come from carbon-12. So the average mass is only about 12.01. We're going to have you calculate some average atomic masses of mystery elements. And the way you're going to do it is we'll give you an abundance in terms of percent. You will take that percent and you'll turn it into a decimal by dividing by 100 or moving the decimal 2 places to the left. You'll multiply it by the mass of the isotope that we tell you, and then you'll just add up all your products and you'll get a weighted average. Anytime you calculate average atomic mass, always give it out to 2 decimal places. So here's an example that's not in your notes, but it's an example that affects you all of the time in all of your classes. When you calculate an average for 9 weeks or for a semester, it's not a straight average. Your homeworks do not count your learning checks do not count the same as your labs, do not count the same as your tests. Everything is a little bit different. And for us, tests obviously count a lot more for your grade. So here's an example. In a class, you have the following grades: a daily grade of 70, which counts for 5%, a lab grade of 85, which labs count for 15, and a test grade of 87 with tests worth 80%. What is your class average? There's a little typo there, that's fine. So if I wanted to calculate your average, you can't just add 70 plus 85 plus 87 and divide by 3. That does not work. That is a normal average. Here, we're doing a weighted average. We're saying that tests are worth 80% versus your daily grade only being worth 5. So when we actually work it out, we're going to say, okay, well, my 70 is worth 5%. And notice I took that 5% and I moved the decimal over 2. In other words, I divided by 100. And I'm going to get a value out of that. My lab grade is an 85 times 0.15. In other words, 15% turned into a decimal. My tests are an 87, and tests are worth 80%. So we're going to get a calculator out, and we're going to get these values. 70 times 0.05 is going to be 3.5. 85 times 0.15 is going to give us 12.75. And 87 times 0.8 is going to give us 69.6. And then we're just going to add those pieces up. You're not going to divide anymore. All you're doing is you're doing this multiplication to weight the different values, and then you're adding them together. So 69.6 plus 12.75 plus 3.5 gives us a final average of 85.85, which, because we're nice, would round up to an 86. That is how weighted averages work. It is not a pretty straight average like the one on the left. You multiply your actual value times the percent and then add up the results. So here's the examples that you're actually going to be dealing with in class. Copper exists as 2 isotopes, copper 63 with an actual mass of 62.939598. And that isotope of copper has a 69.17% abundance. And copper 65, which has that actual mass, has a 30.83% abundance. Find the average atomic mass. So 2 isotopes means I'm going to have 2 percentages and 2 multiplications. Copper 63 has a 69% abundance, which translates to 0.6917. Now notice I have copper 63. Remember that number at the end tells you the mass number. So you could potentially start arguing, oh, well, I know that the mass is 63. But then I go ahead and tell you that the actual mass is 62.939598. Here's the deal. If we tell you the actual mass, like we do here, you have to use the actual mass that we give you. So you're not allowed to use the shortcut of copper 63. You have to actually multiply that by 62.939598. Yes, it could make a serious difference. If we give you the mass, use the mass that we give you. So we're going to do that for the first one. Then I'm going to set up the other one. 30.83 turns into 0.3083. And I'm going to do it by the mass of copper 65, because this percent goes with that isotope, this percent goes with that isotope. 64.927793. And I'll go find my calculator. Here it is, 0.6917 times 62.39598 gives me 43.5353. That, remember, we're rounding to 2 decimal places, so that's about as far as we have to go for the actual calculation piece. And we'll do the second one, 0.3083 times 64.927793, giving me 20.0172. And I'll add those together and round to 2 decimal places, which gives me a 0.54 AMUs. Your average should always be somewhere between the 2 masses that you used. Doesn't necessarily have to be right in the middle. It could lean more one way or another, but it has to be between your biggest and smallest values. We only had 2 values here, so 62.939 and 64.927. So we should check and make sure that that 63.54 is somewhere between our 2 values. Sure enough, it is. So it at least mathematically makes sense. Assuming you typed everything in your calculator correctly, that should be the right answer. Notice we used the right units, AMU. So, one more example. Calculate the estimated average atomic mass of neon if neon exists naturally as 90.92% neon 20, 0.257% neon 21, and the rest is neon 22. So, I have 3 isotopes here, neon 20, neon 21, neon 22. I do not say in the problem the actual mass of neon 20 is whatever. The actual mass of neon 21 is whatever. The actual mass of neon 22 is whatever. If I don't tell you actual masses, you are allowed to use the assumed masses of those different isotopes, 20, 21, and 22. I have 3 isotopes, but in the problem I only list 2 different percentages. Well, if I have 3 different isotopes, I have to have 3 percentages. If I know 2 of them, and I assume that the total percent is going to be 100%, I should be able to say, well, if I take 100 minus 90.92 minus 0.257, I should be able to figure out whatever is the rest. In other words, I should be able to finish that final percentage. So I'll do 100 minus 90.92 minus 0.257, and I'll figure out that the rest is about 8.82 3%. So I have my third percent, the percent that goes with neon 22. Go ahead and pause the video here. Take a few minutes to try to set up and work through this problem. See if you can get all the way to the average atomic mass. The answer and the work is all going to pop up here in just a second. So try to do the work first and then come back and check this. Alright, so if you worked it all out correctly, you set up all your work, you should get to a total of 20.18 AMUs. Notice we have 2 decimal places and we have our units, AMUs. We used our assumed masses here because we didn't have anything more precise. One of the most common mistakes that we see would have been right in here, where it's percent is already a decimal. You still have to divide by 100 in order to get it out of being a decimal. So we see a lot of students leave that as 0.257. Don't forget, you always have to divide by 100 no matter what the percent is that we give you. Notice our check still works. We should get a number between 20 and 22, the biggest and smallest. And you can kind of make a guess. 90% of this isotope tends to be neon 20. So our average should be pretty close to neon 20. And sure enough, it is 20.18. So you can kind of use some logic to check your work. But if you're able to work through the problem, check all your math, make sure your typing's in your calculator right, you should be okay. That concludes our video for average atomic mass. Make sure you're getting those practice problems done in anticipation of your learning checks on your test. And as usual, if you are struggling or if you want more problems, please come see us and we will write up some new problems and help you work through whatever questions you might have.